Your generator is running right now in your mind. That steady diesel growl you've rehearsed as the sound of safety, and it is quietly frying everything you've plugged into it. Picture the garage at 2 in the morning. The grid is down. The air smells like exhaust and hot rubber. The extension cord running through the cracked window is warm to the touch, feeding power into your refrigerator, your freezer, the medical device on the nightstand. Everything looks fine. The lights are on. But inside every one of those machines, something is happening at a frequency you can't see, and your multimeter won't catch unless you know exactly what to test for. Within 72 hours of continuous generator use, appliances with sensitive electronics begin accumulating damage. Not catastrophic, immediate failure. The slow kind. The kind that shows up 3 weeks later when the grid is back and you think you're safe. The U.S. Army Signal Corps knew this problem in 1943. Their field engineers in North Africa watched thousands of dollars of radio and communications equipment die on portable generators, and they built a fix from wire, iron, and principles that still work today. The generator industry has a measurement it prefers you don't look up. It's called total harmonic distortion, and on a conventional portable generator, the kind sold at every hardware chain for between $500 and $1,200, that number sits between 15% and 25% under load. Oddly, some cheaper units push past 30%. The number matters because every appliance manufacturer designs their equipment to receive power with a THD below 6%. That's the threshold. The gap between what your generator produces and what your appliances expect is not a minor variance. It is in many cases a 5-fold mismatch. The Consumer Product Safety Commission has documented generator-related appliance damage in thousands of post-disaster insurance claims. And electricians working hurricane and flood recovery sites will tell you the same thing quietly. Half the equipment that survived the storm didn't survive the generator used to power the recovery. The industry knows. The packaging doesn't say it. The Army Signal Corps didn't have the luxury of replacing equipment in the Libyan desert in 1943. Non-field engineers, men who had been radio technicians and electricians before the war, began adapting a principle already understood in power transmission engineering, that a corrupted electrical wave could be reshaped before it reached sensitive loads. They called the approach line conditioning, and they built improvised versions from transformer cores, capacitor banks, and wound copper, materials they had or could salvage. The fix worked well enough that it became doctrine. It carried into Korea, Vietnam, and eventually into every serious military forward operating base ever established. The civilian world forgot it. Every electrical device in your home, every motor, every circuit board, every microprocessor is engineered to receive power in one very specific shape. That shape is called a sine wave. Picture a smooth, continuous S-curve rolling forward in time. It rises gradually to a peak, falls back through zero, descends to a trough, and returns. That rhythm repeats 60 times per second in North American grid power. Grid operators spend enormous resources keeping that wave clean because deviations from the shape, spikes, plateaus, jagged steps, are what engineers call harmonics. Harmonics are unwanted frequencies that ride on top of the fundamental 60 Hz signal like static riding on a radio broadcast. Total harmonic distortion, or THD, is simply the percentage of your power signal that consists of those unwanted riders rather than the clean fundamental wave. At 6% THD or below, your appliances process the noise without meaningful stress. At 20% THD, a typical conventional generator. Transformers inside your appliances run hotter than designed. The capacitors and switching power supplies charge unevenly. And the variable speed motors in refrigerators and HVAC systems receive torque commands that don't match what the engineers intended. The damage is cumulative. It's thermal, and it's invisible until the component fails. Think of it this way. A quality non-stick pan transfers heat evenly across its entire surface. Every part of the food touching it receives the same temperature at the same moment. Now imagine that pan is warped, with a ridge running across the center. Half the food burns, while the other half sits in pooled oil, barely cooking. The pan is still hot. It still technically works, but the output is inconsistent, stressed, and destructive to what you're trying to prepare. That warped pan is your conventional generator's output wave. The food is your appliance's internal components. A clean sine wave is the flat pan, uniform, predictable, delivering energy the way the recipe was written. The fix works by either replacing the corrupted wave entirely or aggressively filtering it before it reaches your loads. The first method is an inverter generator. A machine that generates raw AC power, converts it internally to DC, direct current, which has no wave at all, and then electronically reconstructs a clean sine wave from scratch before outputting it. Modern inverter generators achieve THD figures below 3%, well inside the appliance safety threshold. The second method applies to conventional generators you already own, an external line conditioner, also called a power conditioner or automatic voltage regulator with harmonic filtering. These devices sit between your generator's outlet and your sensitive loads. Inside a ferro-resonant transformer, a transformer specifically wound to reject harmonic frequencies absorbs the dirty frequencies and outputs a stabilized near-sinusoidal wave. The physics behind this involves magnetic core saturation. The transformer's iron core is deliberately driven into a state where it naturally attenuates frequencies above the fundamental, acting as a passive harmonic filter. No moving parts, no software, no firmware to update. It is an electromagnetic property of iron, and it has been working reliably since the 1940s. For this method, you need either an inverter generator rated for your critical load in watts, outages, or a ferro-resonant line conditioner matched to the same wattage. You also need 10-gauge extension cord rated for the amperage you're running, a clamp meter capable of reading true RMS voltage, not average responding, and a basic grounding rod if your generator will run for more than 4 hours continuously. Make a list of every appliance you plan to power. Find the wattage label, usually on a sticker near the power cord, and note both the running watts and the starting watts. Because motor-driven equipment like refrigerators draw 2 to 3 times their running wattage for the first 2 seconds at startup. Add your running watts together first. A typical refrigerator runs at 150 watts, a chest freezer at 100 watts, a CPAP machine at 30 to 60 watts, phone and device charging at roughly 50 watts combined. That gives you a baseline running load, call it 400 watts for this example. Now add the single highest starting watt appliance. Because only one motor starts at a time. If your refrigerator starts at 450 watts, your peak demand is roughly 850 watts. Choose a conditioner or inverter generator rated to at least 1,200 watts to give yourself a 40% headroom margin. Running any electrical device at or near its rated maximum accelerates wear. When connecting the conditioner to your generator, run the ground wire from the conditioner's chassis to a dedicated grounding rod driven at least 4 feet into soil. This is not optional, and skipping it means any fault current has nowhere safe to go except through your equipment or through you. Plug your critical appliances into the conditioner's output, not directly into the generator. Use the clamp meter set to true RMS mode to read the output voltage at the conditioner's outlet before connecting anything sensitive. You are looking for a steady 120 volts, plus or minus 5 volts. If the reading swings more than that, your conditioner may be undersized for your generator's output instability, and you should run fewer loads simultaneously. Once voltage is stable, connect your appliances one at a time, starting with the lowest wattage device and finishing with the highest. Watch the meter for each addition. If voltage drops more than 8 volts when the refrigerator compressor kicks on, reduce your other loads until it stabilizes. Run the system for 30 minutes, then physically check every connection point. The conditioner's input plug, the generator outlet, the grounding clamp, for heat. Warm is acceptable. Hot means resistance, and resistance means a loose connection you need to fix before it arcs. The performance data on this is not theoretical. Alice. A 2019 study published in the IIEEE Transactions on Industry Applications measured the lifespan impact of sustained 20% THD exposure on switch mode power supplies, the type found in virtually every modern appliance, and found a reduction in capacitor service life of between 40% and 60% compared to units operated on clean power. The U.S. Department of Energy's own efficiency standards for appliances assume grid quality power at below 5% THD. Operate outside that band long enough. And you are not running your appliances. You are consuming them. Inverter generators tested by independent labs consistently measure THD below 3% at 50% load. ferroresonant conditioners tested against conventional generator output reduce measured THD from an average of 22% down to between 4% and 7%, inside the safe zone for all standard residential appliances. The cost arithmetic is straightforward. A quality ferroresonant line conditioner in the 1,200 to 2,000 watt range costs between $180 and $350 new, and older units in good condition appear on resale markets for $40 to $120. A refrigerator compressor replacement costs $400 to $700. A CPAP machine replacement costs $800 to $1,500. A single chest freezer, should its control board fail, runs $600 to $900 to replace. You will spend the cost of one conditioner and protect equipment worth 10 times that figure. Equipment you may not be able to source quickly when the supply chain that delivers electronics to retail shelves is under pressure. The inverter generator path costs more upfront. Quality units start around $500 and run to $1,200. But they are also quieter, more fuel efficient, and produce cleaner power without any additional hardware. The signal core solution held up in the field for the remainder of the war and continued in military doctrine for decades because it worked on the physics, not on the brand. Engineers at forward operating bases in the 1960s and 1970s were still using ferroresonant isolation transformers to protect communications gear from generator noise. Today, on data centers, the most power-sensitive environments on the planet use the same harmonic filtering principle at industrial scale to protect server infrastructure from grid fluctuations. The principle that kept a field radio alive in Tunisia in 1943 is the same principle protecting a $40,000 server rack in a climate-controlled facility right now. When the supply chain that feeds replacement electronics seizes up, the gap between a ruined appliance and a working one will not be measured in money. It will be measured in whether you knew this before it happened. Your generator is not your backup plan. The way you condition what comes out of it is your backup plan. You either protect your equipment with the same thinking that kept wartime field communications alive under fire, or you trust that the hardware store will have what you need after the next extended outage. One of those options is inside your control.